So the next talk for today's session is on memoristic computing, and the talk is given by Professor Dhireesha Kurtipudi, and I'll give a brief introduction about her. So she is a professor and founding director of the AI consortium with the University of Texas, San Antonio, and Robert F. McDermott Chair in Engineering. Her research interests include neuromorphic AI, low-power machine intelligence, brain-inspired accelerators, and use-inspired research. Her team has developed comprehensive neocortex and cerebellum-based architectures with non-volatile memory, hybrid plasticity models, and ultra-low precision architectures. She is passionate about transdisciplinary and inclusive research training in AI fields. She is the recipient of Claire Booth Luce Scholarship in STEM for Women in 2018 and the 2018 Technology Women of the Year in Rochester. And over to you, Professor Dhireesha, for the presentation. Thank you.
Thank you very much for that kind introduction. Good evening, y'all, from Texas. So in today's talk, I'll be presenting more on the neuro-inspired AI accelerators that support online and continual learning. As the introduction went, I will cover how we use memristors within this accelerator, but I will not go in detail into the fundamentals of the memristor because I know there are several other speakers throughout this school that are presenting in depth in details about the memristor operation. So for this work, the student contributors are Abdullah Ziara, Fatima, Zohora, Vedant, and Anurag. They are the brains behind some of this phenomenal work. So before I go into the research, I want to introduce a little bit about our research lab. It's the Neuromorphic AI Lab, and our goal is to design the next generation of computing systems that can perform natural tasks, which typically require human intelligence. But most importantly, we want to do it in the most energy efficient manner. So for this, we really frame the research questions that we are working on currently into two categories. One, can our understanding of human neural processing and perception lead to new AI algorithms and hardware advances, which is kind of what I'm going to cover in today's talk. And also, can we design AI that learns continuously through its lifetime? And can we do this in an energy efficient fashion? So in order to achieve this, we really take a multidisciplinary approach. In a sense, on the cartoon that you see on the top, we work very closely with neuroscientists and computational neuroscientists in trying to understand the different plasticity mechanisms that are observed or studied in the human brain or other brains, and take abstractions of these plasticity mechanisms and emulate them in algorithms and to solve different types of tasks. As I said, tasks that require human intelligence. And from there on, we design the hardware because at the core, a large group of the students in our research group are computer engineers. So we do design hardware or accelerators from there on. So before I go further into what we work on in our research lab, I want to talk about what is really so interesting about the human brain. Again, this is from a computer engineering point of view. If we look at it, we like to crunch these numbers. We have about 100 billion neurons, and you see 200 neuron firings per second, and there are 1,000 connections that happen per firing. And what does that really translates into the compute, especially when we are looking at the calculations per second? It's about 20 million billion calculations per second. That's an amazing feat. So if we kind of look at it in a computational term, you can think of it as the brain having these 86 billion cores, where each neuron you can think of as a computational core. And the total power dissipation is only about 20 watts, and a lot of it is during the resting state. And it is debatable whether it's 20 or 25 watts, but it's still really, really low power consumption. And similarly, the memory, several neuroscientists have addressed that it could be up to 2.5 petabytes of memory. And of course, we all know that the area or the size of this is really compact. And maybe the core processing unit is the neocortex to make all those decisions of higher order intelligence. And we don't know what the operating system is. I mean, if you ask a neuroscientist, they'll say we still do not understand quite a bit about the brain, but there are these higher level inference that are drawn to kind of see, well, that's really interesting. It is able to do this amazing amount of calculations with very minimal power. And if you really look at why, okay, it is amazing that it is able to do these computations, but why are we so excited about designing neuro-inspired AI systems, or why we want to have neuro-inspired learning? So if you really look at the brains, they can process a lot of information with very minimal resources. What I mean by that is that they're working with unstructured data. If you look at around yourself in the real world, right, you're constantly processing information from different modalities that is really unstructured, and it's often referred to as dark data. And it is coming at different frequencies at different times, and it's still able to process it very, very efficiently and with very few glitches. So it's an exemplary complex system where, if you think about the functionality, it is emerging as a global property with several of the local mesoscopic and microscopic interactions. And the other beautiful thing about the brains is that they're plastic at all levels of abstraction, in a sense, from neurons to the skull, and from right from the time of inception. So this kind of gives them this ability to learn continuously, which we often refer to as lifelong learning. And I mean, some of us might debate whether we are learning continuously through our lifetime when we become older, but there is this neurogenesis and other plasticity mechanisms that are happening in our brains so that we are able to learn continuously. And the other interesting factor, as a circuit designer or as a hardware designer, many of you might be here attending this summer school. The beauty of it is that it performs all these computations with unreliable or stochastic primitives. Rather than unreliable, I would say stochastic primitives. So it can extract information out of noise, and it can achieve precision through this parallelism and redundancy. They appear to compensate for this stochastic primitives in some form. So in the end, it is able to learn in a very robust fashion. And they're very learning centric, as in with both spatial and temporal information. And they also work very well with imbalanced data samples. As in, you might have seen some animal once in your lifetime when you are 5 years old, and maybe if you encounter that animal, there is an ability for you to still process and recognize that this is an animal of a certain type. So, it has this amazing ability to work with one shot or a few shot learning, or having fewer data samples. So in summary, natural intelligence or neural inspired learning or AI systems can offer us insights that we would otherwise miss. So then I would reframe the question as, why not take inspiration from this system as we build the next generation AI? So this is not something just our research lab is looking at, and as some of you might be aware of who are working in neuromorphic computing, Carver Mead had this thought, coined this term neuromorphic computing, and even in his research article, he has explicitly stated that for many problems, particularly those in which the input data are ill-conditioned and the computation can be specified in a relative manner, biological solutions are many orders of magnitude more effective. And in the context of neuromorphic computing, we are taking or emulating the actual biological mechanisms and putting it on silicon. But there is this emerging group of researchers from multiple organizations that are looking at brain as a source of inspiration to build the next generation of AI systems, including Google's DeepMind, which is one of the phenomenal research group where neuroscientists, computer engineers, computer scientists, electrical engineers, and are all working in a collaborative fashion to build these comprehensive AI algorithms. And this is the quote from Demis Hassibi from Google's DeepMind, where they kind of really position themselves as looking at this human brain to build the next generation of algorithms, particularly to achieve the general intelligence we're all striving towards. So yeah, if we look at the capabilities of these neuro-inspired algorithms, or in this context, I'm covering some of the things our own research lab is working on. We could divide them in terms of the algorithm types or capabilities and the type of tasks they're learning. So on the x-axis here, you see the different brain regions, whether it's the sensory cortical regions, the recurrent regions, the neocortex, and so forth. And if you look at the deep convolutional neural networks, which some of you are perhaps very familiar with, they take abstractions from the visual cortex and visual cortex primarily, and are able to solve several spatial tasks very efficiently. And if we look at the recurrent regions of the brain, there are deep recurrent neural networks that take inspiration from there and are able to solve both temporal and spatiotemporal tasks. And there are these specific algorithms that are inspired by the different cortical and subcortical regions within the brain. For example, the neocortex inspired algorithm, which I'm going to talk about today, the hierarchical temporal memory, takes inspiration not only from the cortical, but also some of the subcortical regions in order to process information in an online fashion. And similarly, we have cerebellum-inspired networks, which I'll not have an opportunity to talk today. And if we go into further advanced algorithms, like for example, if you want your algorithms to learn continuously, you perhaps have to abstract beyond looking at cortical regions. You might have to abstract different types of plasticity mechanisms into these algorithms to achieve these self-organizing capabilities. So with that intro, I just want to quickly summarize what we are focused as a research team right now. So we look at neurally inspired algorithms. We look at both spiking and non-spiking neural networks in that context. And as I said earlier, we are interested in how to make our systems learn continuously. We use different types of plasticity mechanisms and dynamic algorithms. This is part of a large effort with DARPA and Air Force research labs. And we are also interested in doing all of this in an energy efficient fashion. So a couple of techniques that we are very much focused on are model compression, such as quantization techniques, and circuit and architecture optimization. And we are doing this with emerging devices, which is where the neuromorphic computing really fits in, using memristors for almost 8-9 years now. We do both digital and mixed signal design. We started exploring emerging technologies with some of our collaborators, such as photonics and FEFETs. And again, these devices are not our expertise. We are working at an abstraction about that. So you can see that we are spanning from across the stack in some sense, from the algorithms to the circuits and architectures. And it is not really possible for one research lab to have strength across all these abstractions. So we really do collaborate very actively with multiple research labs who give us insights at the neural processing level, or they give us insight at the device and fab level, and so forth. So this is a team of researchers that really work and have fun doing all this work in the lab. And at the bottom is one of the chips that was taped out a few years back. And then we just taped out our new chip literally last week. And students were working really hard, though it looks like they're playing here. They worked really hard to get this chip taped out recently. Okay, so coming to what I wanted to highlight in today's talk, particularly building these accelerators for continual and online learning, we really have to, if looking at the field today, one of the reasons we want to have these capabilities in the AI systems is because of the applications, the dynamic spectrum of applications that are demanding capabilities where the system needs to learn continuously. They want real-time and rapid analysis on the data that is being collected. So I think there were several talks perhaps earlier today that covered why it is important to do this in a very size-constrained and energy-constrained environments like the mobile devices. It's a rapidly growing market, and you would want to make these decisions on these edge devices or on these platforms in a dynamic fashion. Or whether we look at the self-driving cars is another classic example. So there are a multitude of applications that can really benefit with this kind of features. But unfortunately, we do not have algorithms today that can perform these continual and online learning tasks efficiently within these constrained environments. There are definitely algorithms that can, if you're not compute bound or if you're not memory bound, there are definitely algorithms that can be deployed on large-scale computing systems. But when it comes to these constrained environments, it's been really challenging to have algorithms that can perform lifelong learning. And lifelong learning is a problem that is still being solved in the algorithm community as well. So if we look at the limitations that are coming in from these devices, it's the size limitation, the memory limitation as to how much you can store on device to do this learning continuously. Of course, there is the power constraint and the communication bandwidth constraints, whether it is inter-device, intra-device, and so forth. And if we look at, those are all the resource limitations. And if we are looking at the compute limitations, of course, there is issues with processing this multimodal data efficiently. And you want to address the latency because you want to do this rapidly or dynamically, depending on the mission criticality of the task you're trying to solve. And the ability to parallelize some of these compute in a time-bound fashion. So all these challenges are there currently. So these applications are in some ways driving innovations in the architectures and systems in this case. Just like giving a little bit more context, how do we enable this kind of intelligence, like to give specific examples in this case, like, you want to dynamically capture the from the wearable devices, different kinds of information about this athlete or a runner, or how do you protect or deliver resources to different environments using these drones, and how do you ensure that you are being safe and secure in terms of using these self-driving cars in different types of dynamic environments. So beyond what I'm going to talk about, there are other issues that researchers are looking at in terms of privacy, reliability, and other things, efficient use of network bandwidth, and so forth in this context. But really what I'm going to cover today is how do we handle continuous learning in these scenarios. And I'm going to show it more from a hardware perspective, and the examples I'm going to show are probably not going to be as exciting. From the algorithm level, we have like pretty exciting applications, but what I'm showing is more from the hardware today, because that is what is more relevant for this specific community. So all these applications are really driving us to think hard about how we are going to design these systems. So the idea is that maybe neuromorphic computing systems, Neuromorphic systems can come to the rescue in this context. And as I said, Carbon-Mead defined this as analog, digital, or mixed-signal VLSI systems that when he defined it, he said to mimic the neural processes, but today the field has become broader where we either emulate or mimic neurobiological processes or neural plasticity mechanisms or neural processing. So if you're looking at articles that kind of use this term more liberally, it is because the field itself has grown so much today that researchers call both levels of abstraction as neuromorphic. So, well, yes, it can solve some of the issues that we have in this continuous learning and deploying those in resource-constrained environments because of inherently having this plasticity embedded because you are abstracting or mimicking the neural processes. And quite often, because you're putting it on silicon in kind of using this a specific type of hardware, for example, the memristor type of hardware, where you have the ability to co-locate memory and compute very closely. So that kind of reduces some of the communication bandwidth issues that I was talking about. And also, because you are emulating these neural processes, you are able to process spatial and temporal information in a dynamic fashion on device. So you can do that in situ learning. And inherently, depending on the type of hardware that we choose, for example, the memristors, we would have a very energy efficient implementation in here. So there are several chips out there in the market today that are emulating this neuromorphic processing at various degrees. Some of them have on-device capability, some of them can learn on the device, some of them cannot. Intel's Loihi or the Pohoku, the newer versions, are able to learn on device, so it has more capabilities to implement different types of algorithms, and you can implement both spiking and rate-based algorithms on these chips. And there is an active group of community that is working very closely in advancing these neuromorphic systems. So, well, we have these chips. So does that mean we are able to kind of address all these challenges? Well, still, it's in phase one or generation one of these systems, or generation 1.1 at this point. In a sense, we have these chips that are able to learn efficiently, but I think scalability is still being a challenge, for example, in one way or the other. And that's what researchers are focusing on right now. And Spinnaker has been able to show some interesting results in terms of scalability, and Intel and IBM, they're all focusing on that. The von Neumann bottleneck in the compute domain, perhaps we've addressed to some degree, but I think if you're using underlying, for a lot of these chips that I've shown here, they're still using underlying CMOS. And it's not going away in some sense. So the von Neumann bottleneck is still there. And in several contexts, I think people have demonstrated it on spatial tasks. And I think more newer examples have started looking at temporal tasks. And it's whether you can learn on device and whether you can implement really dense networks or sparse networks is all varying across the neuromorphic processors. And in some ways, the plasticity mechanisms that you see on these chips is also limited. There are fewer neural plasticity rules or neural models that can be implemented today. Again, it's being updated as we speak. Researchers are trying very hard to support heterogeneous plasticity mechanisms on these chips, but there are some of these challenges that are still there, and the co-design frameworks are being developed. There is no one single framework. Everybody said, okay, let's use this specific framework similar to what you would see in machine learning community. And there is no specific agreed upon set of data sets that everybody is working towards. So that's all being developed as we are speaking. So excuse me, in order to kind of design these systems, we use, as I said, different emerging technologies. And in this talk, I'm going to highlight the memristor and CMOS-based architectures. I'm not going to go too detailed into this, but one of the early models that we used was a tantalum oxide memristor device, which was fabricated at Sandia National Labs in some of our early models. And we used copper oxide and hafnium oxide devices as well that were fabricated at SUNY Poly and in some of our other architectures. So in a sense, like we get these device parameters from our collaborators and use them to design more realistic circuits. And from there, we kind of take that into building the accelerators or architectures and send to tape out in some scenarios. So we have both synapses and neurons that are designed out of these memristors. There is, if any of you are interested, we can share the relevant papers on that. So the most common architecture that we use with these memristors is a crossbar architecture, and that's what is used in the first accelerator I'm going to talk about. Okay, so with that, there are two neuro-inspired accelerators that I'm going to talk about today. The first one is called Pyrogrid, and the second one is Metaplasticity. So Pyrogrid is really a neocortex-inspired accelerator and architecture. And if we look at left, it shows the neocortex with its 6 layers. So you can see this is a very dynamic structure with different types of neurons. If you can, I don't know if you can see my pointer. Let me try for a pen. So you can see that there are these large pyramidal neurons in some layers. And you could also see that there are inverted pyramidal neurons and medium pyramidal neurons and so forth. But the underlying core neuron is that pyramidal neuron. So there is a lot of redundancy in that. And there is sparseness across the layers. But this is one of the core unit within the neocortex. And how you're communicating across the layers and how this whole neocortex is communicating to its subcortical regions like the thalamus are all guiding us in how we design this algorithms. So this specific algorithm that I'm going to talk about is called the hierarchical temporal memory algorithm that came out of Numenta and designed by Jeff Hawkins, and it's still being developed and evolving. So we work very closely with that group in trying to kind of capture the newer dynamics of the algorithm into our architectures. So when my students started looking at designing an accelerator for this, a lot of this work I'm going to present on Pyrogrid, or most of it is from Abdullah for his PhD. And his focus was on designing really this low latency and energy efficient neuromorphic system, which can process spatial and temporal information. So the system is able to support on-device learning. Of course, it's neurally inspired, not just because we have the neocortex as a source of inspiration, but also he has introduced new plasticity mechanisms in this model, such as neurogenesis, to make it more robust in terms of learning. And it is able to do real-time processing and has a very dynamic structure. So if you look at this cartoon on the right, you can see that there is external world or sensory information that is coming in from the external world that is being processed by an encoder. And that encoder kind of cleans up your data and kind of feeds into the network. And based on how it is processing this information, you can use it for detection, such as anomaly detection in real time or in an online fashion, or you can do some kind of prediction. And the cartoon on the left here is just showing that the algorithm is taken and we kind of build the, the algorithm is built from the plasticity in the brain, and then we kind of build the chip and it is deployed into this environment. So we are at this phase. I don't think we will see that real world deployment because we are an academic lab. So if you look at the neocortex in here, in the context of the brain, you see it in here, that, and you zoom in and you're seeing this region, and within that you're seeing that pyramidal neuron. So HTM algorithm as such is structured from ascending hierarchical regions of the cellular layers that enable the network to demonstrate the strong capability in processing both spatial and temporal information. So the structure of this algorithm, if you see it, the cells in the HTM are a simplified model. The cells which I'm talking about are a very simplified model of this pyramidal neuron. And we group these cells into calling this mini columns. I apologize for the background noise. And similar to pyramidal neurons, HTM cells have hundreds of synaptic connections that enable them to recognize independent patterns of cellular activity. And there are different ways in how this information is integrated, whether it's in a proximal, just like how you see in this neuron, you could have these connections very close to the cell body. They could be further away from the cell body, which is called distal or apical. So depending on where it is located, you would have those zones. And the same approach is used in how this architecture is designed. So if you see the bottom figure in here, each cell is represented as this cylinder, and you would have multiple of those cells that are forming a mini column. And the nearby cells, we are calling those proximal connections, and farther away, we are calling those distal connections. And you could have multiple levels, level 1, level 2, up to level 6. But most of the capabilities that we have seen with this algorithm right now are at a single level. So if we divide the core operations of this algorithm, you can divide them into spatial pooling and temporal memory. In the interest of time, I won't go too detailed into these operations, and I'll be happy to share the specific research articles, but I want to give you a high-level concept of what's happening with each of these operations. For the spatial pooler, we capture the spatial patterns and transform the input into something called a sparse distributed representation. So, and the way it is done is by really looking at selecting a set of active mini columns to represent the input. And the mini columns are nothing but, again, these blocks that you're seeing here, and each cell is representing that pyramidal neuron. So basically, for the example here, you could have, for example, 4 that is being fed in from the external sensory unit, and that is being encoded, and we are transforming that into the sparse distributed representation. And within that, the phases of operation, in a sense, you could have initialization, where you're drawing the receptive field of each of these mini columns. You could have the receptive field defined right now, but in general, it's a very dynamic factor. So depending on the type of task and the system you're designing, the receptive field can be defined today. And similarly, you assign permanence to some of these connections based on what input is being fed in. And then you use mechanisms such as overlap and inhibition to calculate how much of the overlap is there with the current input, and whether you have to inhibit that signal or not. So based on that, in this phase, in this learning phase, your mini column can be in an active state or in a nominated state or in an inactive state. I know there's a lot of terminology that is coming in here. If any of you are interested, we'll be happy to share that information. So that is what's happening in the spatial information. You're essentially converting that input into that sparse distributed representation, so you're preparing that for the network to learn from that. And sparse distributed representation is a very robust form of representation, in input data representation, because in brain it is considered only 2% of the neurons would be active at any given time. And Here, similarly, we would have only 2% of the bits that are active. So they kind of take that inspiration from the biological processing to have that robust representation. And once you have that, you take the data and try to kind of see whether the temporal context of the information, because earlier we were only doing the spatial part. So in the temporal context, there are two different scenarios that can happen. One where you have seen this input a prior and it is coming back again, and you are able to, you as in the HTM is able to quickly recognize what that input is. Or in the other context where it has never seen that input before and or the sequence before, and it is coming up now, and how it is going to learn and activate different cells within that. So basically, that's how it kind of recognizes. If it's a known input, it activates that specific cell, basically. It evaluates those mini columns and that specific cell to kind of evaluate that pattern. And if it's an unknown input, the idea is that it shouldn't need significant number of new samples for it to kind of recognize it when it happens the next time. So it kind of has that few shot learning capability, as in it's able to see the input only a few times, but it's able to robustly recognize when it comes back again. So again, all of this processing is happening at a single level, whether it is the spatial or the temporal processing. And when the higher levels are activated, there is more capabilities that this algorithm can have in terms of learning. Okay, so with that background, what you might be more interested in is how we are going to design the system from there. So after understanding the algorithm and working with the core group at Numenta and several other researchers in my lab, the students, we have identified that there are a few bottleneck operations that are memory hungry, or they are not very efficient in terms of computation. So if we look at this cartoon again on the left, computation-wise, computing that overlap or evaluating the segments is expensive. And if we look at how well we can parallelize the operations in our architecture, we see that inhibition or online training and again overlap are some bottleneck operations that we really need to look at on how to parallelize them. And there is also dynamic structure to this architecture, as in there is new synapses that are going to be generated through the network's lifetime, or new neurons that are being generated through the network's lifetime. In HTM's term, they call it potential synapse. So there is the potential that the synapse could be generated at a later time. In hardware, you are already thinking, right, how you are designing for a specific number of synapses or neurons. So how are you going to capture or encapsulate this concept of a potential synapse, or something could be generated in the future? So that's another interesting challenge. And if we look at the cost of implementing these units in some ways, like, you know, the computation cost or so forth, or the memory access cost, it's pretty expensive if you do not optimize it at the beginning. And this Horowitz paper that is well cited in terms of the cost of this memory computation for 32-bit DRAM read, you are consuming close to 1,000 picojoules. And I believe this was in 32 nanometer node or 45 nanometer node. So it's a very expensive operation, and you want to reduce that accesses and also the storage. And even if you look at the compute, a 32-bit add is not cheap. So you want to reduce those compute operations. So one way we look at to kind of reduce this is using something called address event representation. It's a very conventional approach if you are in the neuromorphic community or in some form earlier learning accelerators in the 80s. I think this is a very conventional approach. you take address event representation. It takes advantage of the sparse neuronal activity and high bandwidth in VLSI systems to enable time multiplex communication. So the challenge for us was how AER can be suitable for HTM structure, because HTM is not directly aligned to realize AER for us. In a sense, it has to support this synchronous dense network, and it needs to support this interchip communication. So we had to kind of come up with an enhanced AER version where we have this virtual description for these distributed memory units. And the other challenge, which I talked about, where there is a chance of these synapses that could potentially happen in the future, or neurogenesis that could happen in the future. For the synapses, we use something called the idea of synthetic synapses, or SSRs. The idea is that synaptic connections are generated as needed rather than stored, so that we use less memory. And we also have high transmission capacity in here. We use memristors, memristor crossbar architecture in realizing these synthetic synapse representations as well. And it supports communication within the chip. So this is kind of the overall architecture for the Pyrogrid. On the left is the top level architecture that you see, that we have this centralized router and these core processing units that are all dynamically communicating, and the input-output bus that you see there. On the right, you see a much more detailed purview of this architecture, where we have this main control unit that is communicating with these different processors, and each of these blocks that you see is a cell, and each mini column supports multiple cells. Again, today the number of cells we support is different, but depending on the type of task we are doing, this is a scalable architecture. We can increase the number of cells dynamically. So that's why we call this a dynamic structure, even in that sense, beyond the synthetic synapse representation. And it's very energy efficient, as I'll show in the results. We designed the mini column itself. We had to take several design considerations into we had to consider several factors as we are designing this, and we use, like when we are computing these proximal units, we use memristors in there, and we use LFSRs in some context to kind of reduce the overhead. As I said, we would be generating those connections rather than kind of storing them locally. And we use a winner-take-all circuit that has less data movement and less storage, and we don't use digital comparators. So overall, that every unit that we design, we have to custom tweak it so that it is able to give us that overall efficiency we need for the system. So when we are trying to do matching with this architecture, we have 12 times less memory, and the concurrent inhibition is able to give us significant speed up in our processing. And if we go further down inside, so I'm coming top down, right? So if you go further inside into this HTM cell, you can see that the cell consists of quite a few digital circuit, but it's kind of, is supporting that synthetic synapse representation. So it supports sparsity and it's dynamic. And because we are able to reuse the data, we again reduce the data movement and get significant speed up with this implementation. And the high speed is coming from the synaptic connection tuning, and also because we are able to parallelize some of the activities in the inhibition. So because of this specific design module, we are able to get reduced 134 times the data movement compared to the baseline architecture, and also reduce the memory. And the underlying memristor that we have chosen hasn't been easy, because for HTM, because of the type of operation that we needed a very specific type of memoristive device. At the time, we weren't sure if there is such a device available, but we were able to find a couple of groups that fabricated this device model, and we were able to kind of build a model for this device that would help us in kind of translating to this large-scale architecture. So on the left, you see the device, the physical device data points, and the actual device model, which was in vTeam. And it's a model that is built with a window function to enforce the nonlinearity that we would like to see so that it fits well with the characteristics we want. So for all our simulations with this architecture, we have used this specific crossbar. And the training that we used, as I said, we are doing in situ or on-device training. So the training system that we have has a single layer, and it is trained with stochastic gradient descent. We used 1T, one transistor, one memristor model in our crossbar structure to avoid the sneaky paths and to get precision in our training. So we use some local control units to kind of adjust the memristor device conductance and at all these cross points. So we call this training unit as Jigsaw, and we have both a local and global controller as well. And we do not need multipliers in this implementation, and we are sharing resources. Because we are using the stochastic gradient descent, the combined effect of the network error that we are calculating and the input that is applied through the writing circuit and pass transistors is reduced. So it's kind of a semi-simplified implementation of the stochastic gradient. And we were able to just fabricate this portion of the architecture, not the entire chip. So we call this Aurora chip, which was, I think, a few years back at SUNY Poly, and just the training part of this system. And this is the test setup that happened at Rochester Institute of Technology, where our lab was located earlier. And because of the complexity of the circuit, we were at that point not able to fabricate the entire chip. It was only the training circuit with on-device learning. So some results from this accelerator system. We've done testing on image recognition task, whether it's MNIST, which is handwritten digits, several of you might be familiar with, and Yale faces with different expressions and shadows and other effects that you see on the bottom here. And in both the contexts, I think our work was able to show pretty decent accuracy using the actual classifier that was there in HTM, rather than using different types of classifiers like support vector machines, which earlier implementations have chosen. And we were able to do that with very few columns. And even in the context of Yale faces, we had pretty decent accuracy that is comparable to other implementation. We also did it in a time series data prediction. This is a Hodgkin data set where the total number of samples are 4,390 and sampled every hour. And we use MAPI as a metric to evaluate the efficacy of this prediction. And essentially, the goal of this prediction is to predict the power consumption for the next 2 and 5 hours. So you can see two different implementations in here. The hardware is what is HW, and the HTM software for 2 hours and 5 hours. So the software, obviously, you can see that the MAPI is very low. It's done really well. And even in the hardware, for 2 hours, the prediction was pretty good, and 5 hours, the MAPI has increased a little bit. But overall, the MAPI, you can see, is decreasing over time. That is really good. We also evaluated the robustness of the network, and we looked at different types of noises introduced into the system, Gaussian and uniform. And we see that there is still a pretty good reduction in the MAPI as we plot the SNR with the MAPI. And we look at what happens if, for the robustness of the system, what happens if these devices get stuck at falls. And you can see that the MAPI here in this case is reduced when you incorporate stuck at falls from 5% to 30%. In some cases, probably for some devices, it might be unrealistic to have such high stuck on falls, but we just wanted to see what is the impact. And stuck off has really marginal impact on the system's ability to learn. We also looked at what happens if the memristor device endurance is of a certain level and how well this architecture can learn over a time frame. So these are the metrics that we use for endurance and learning. And we see that we got about 8 years of successful learning. And it is kind of 24 times more than conventional networks with no sparse activity. And we kind of did it with different column sizes as well. And we see a similar pattern or consistent pattern across them. And we also measured the latency of our design of each of the individual units. And we see that there is improvement with, of course, going to mixed signal design. I don't have to preach to the choir here, all of you know that. But we just wanted to see what's the level of improvement we get with the mixed signal implementation, where it uses the memristor-based one, and we got about 2x improvement. And we did also the power analysis for this system. We got about 29 milliwatts, the average power consumption for these different operations in HTM. And you can see that there is these peaks that you observe. And these are happening when certain operations are triggered, like, for example, when the proximal unit is on, and we are looking at, you can use kind of creative techniques from the low power circuit and architecture design to kind of address these challenges very easily. And that's what some of the students are looking at. Overall, we kind of reduce the power significantly by using this memristor-based approach compared to the pure CMOS implementation. If we have to compare this architecture with state-of-the-art implementations, in the interest of time, I will skip this, but we've kind of compared extensively in literature with, actually, Dr. James has also done some very interesting work in this space. So we compared these different designs and saw, like, for example, in terms of power consumption, how well our design does. But in this context, you can see we have, this is an unfair comparison, the GPU implementation. It is going to be power hungry. But because some of the reviewers requested that comparison, we plugged it in there, even this i7, because these are power hungry compared to these custom designs. So we really have significant savings with this implementation. And we see some kind of linear scaling as well. And similarly, we did that comparison for latency, and we got pretty good results in terms of latency compared to the Pyrogrid. The other systems have significant overhead in terms of latency. Again, as I said, the Core i7 and the Tesla GPU are unfair to be plugged in there. And if we look at it in the big context, because we started off saying these applications are driving force here. So if we look at that big context and see, look, the power budget we have for these devices, HTM Pyrogrid really fits pretty well for those edge requirements. You can categorize them into different capacities, level 1 to 5. And HTM pretty much goes on that level 5, where it's up to tens of watts. So it is able to satisfy the needs. But again, there are even more, there are newer class of devices that are going to emerge, tiny edge devices or tiny machine learning devices that might be needing to operate even under lower power budgets. So it can benefit from further power reduction. And for those of you who are interested, this is like comparison of HTM with other relevant work in this space. With the interest of time, I'll skip this. Okay, so that was the neocortex inspired architecture. I don't know how I'm running on time. Are we good?
I think almost maybe 5 minutes.
Okay, so I'll rush through this.
That's okay. Yours is the last talk, so for the day, so it's fine.
Yeah, I know. I don't want to keep up people. I know it's pretty late in India right now. The second part of the architecture I wanted to talk was about metaplasticity inspired network. This might be of interest to you more in the context of why we were looking at metaplasticity. So I'll give you the context and probably not go too detailed into the architecture. But when you look at traditional conventional AI networks, they really excel on a single task. Like when you have a task 1 or a single task 2 or a single task 3, they might be doing an amazing job. But when you have a sequence of tasks, which it has to learn continuously and perform well on those tasks, for example, it learned well on task 1, it did well, task 2, it did well, and task 4, it did well. And then you reintroduce task 1, you would expect it to do what it did earlier, but then here you see that it is not doing what it's supposed to do. And that is because it catastrophically forgot what it learned before. So it's called catastrophic forgetting. And that's a serious problem because in real world, you would have these different types of tasks that are being continuously fed into a system. So there is different research groups which are using multiple plasticity mechanisms to address this challenge. In here, we are using metaplasticity to reduce that catastrophic forgetting. So what exactly is metaplasticity? So I'll skip through this slide in the interest of time. Metaplasticity is nothing but plasticity of plasticity, of synaptic plasticity. So you all might have heard about synaptic, single synapse plasticity, but which follows like Hebbian learning. But metaplasticity is a term that was coined by Abraham and Baer, where it refers to the plasticity of synaptic plasticity to different synapses. And all of them are controlled by the same mechanism. So on the figure here on the left, this was experiment done on the hippocampal region of the brain. You can see all these group of synapses are being controlled by the same mechanism. So what it does is that it kind of, depending on the activity that is happening at these different synapses at the same point of time, the neural function is modulated, and therefore the synaptic plasticity will be modulated, which will lead to long-term potentiation, which is called LTP or long-term depression. So that's a very interesting phenomenon. So now you're not looking at a synapse as just a transmitting device or a modulating device, but these group of synapses can form these complex processing units by themselves. And there is interesting work by Dr. Fusey if you want to look at how these complex synapses can help in this catastrophic forgetting. So what we did was there were earlier models that kind of capture this complexity in this synapses or metaplasticity of the synapses. The cascade model or the serial model, as I said, you can look at Fusey's work. What we did was just added probabilistic nature in the transitions of these synaptic states. When it is transitioning from one state to another, there is some kind of probability through which it is going to transition rather than having equal probability across the transitions. So what this does is it kind of makes the higher states or higher meta states more stable, while those at lower meta states will be more plastic. And what happens is in machine learning training scenario, input samples are presented multiple times over multiple epochs, and you are able to retain previously learned information with high stability in the synaptic model. So that is how it is able to address the catastrophic forgetting. So we kind of designed a model for this using a single layer architecture that is very lightweight, and we designed a systolic array based architecture with output stationary data flow and able to demonstrate that it learns continuously across different tasks using something called a domain IL scenario, domain independent learning. If you're interested, there are different types of scenarios in which you can test this continual learning, and that's what we did. And we got pretty good results for this metaplastic net that we proposed. So our work shows that it outperforms other binary models on the split MNIST task, as well as on the MNIST and fashion MNIST task, which is just nothing but clothing, which is a slightly complex task than MNIST. So in other words, we introduce MNIST and then fashion MNIST and then MNIST and see how the network performs on that. So, and in terms of resource utilization, it is very efficient because we replace multiplication operation with simple accumulations, and we just have one fixed point comparison. So the order of time and space complexities are lower for this network. So I presented two different types of architectures. One is neocortex inspired and one is more metaplasticity inspired. Both of them show learning capabilities on small tasks, as you can see, on simple tasks, and we have scaled up the operations on the HTM and C, still consistent performance on complex tasks as well. And on metaplastic net, we have metaplasticity and other plasticity mechanisms that are induced into a network and see good performance that just came out in an ICML workshop last week. So thanks to all the sponsors who have helped us through various phases of this project, and this amazing team that does all the work behind and has some fun occasionally too, sorry. And we are looking for students at this point to join our lab, and if any of you are interested, please do reach out. With that, thank you so much for your time, and thank you for staying up this late in the night. I'll be happy to take any questions.
Yeah, thank you. I think there is one question, but I'm not sure whether it's very strongly related. What is the difference between FE FETs and negative capacitance FET?
Oh, I think I would defer that question to Santosh, because the FEFET devices that we are using, yeah, I would defer that question to Santosh. I think I'm not an expert on FEFET devices at all. It was more of the parameters that we have used from the FEFET devices that were fabricated by Santosh. I don't know if you're familiar with Dr. Kurnek's work, but it's been a year and a half since I looked at these devices, I believe, almost. So I would defer that question or answer you for sure offline.
Yeah. Just another question, like, did you face any non-idealities in your, how much of that really affected your simulations?
Yes, definitely. I think the device the memoristic device that we were looking at was very challenging to work with per se, because it was not a device that for the HTM architecture specifically. So that's why even in our testing and evaluation, we have done a lot of analysis with noise induction into the network, both uniform and Gaussian, and see how well it does. And so in general, there are two aspects to it, right, Alex? If you look at it, you could have like the robustness coming from the choice or the nature of the algorithm itself. So in some ways, HTM is giving us that robustness. But to what degree can it give, right? If 50% of your devices are failing, then can you still get that accuracy or performance on that device? Or if 30% of your devices are failing, can you still get that performance? So that's kind of the analysis we did with that uniform and Gaussian distribution. And we saw that there is like this sweet spot, maybe 20%. You still kind of, it tapers, but still you could get a decent accuracy. So
did training help at all?
Sorry?
Did training the network further help? So from the preliminary set of like non-idealities, that you would have. Did you
Yes,
retrain the network or?
yes,
Yeah.
yes. Yeah, that is the advantage of doing that on-device training, right? You are incorporating that non-idealities dynamically into your training process. Yes, so that definitely helps. And I've seen that this work even better in the cerebellum-inspired architectures where they were able to take, I think, failures up to 25 to 30%, and you would just have a drop of 2% in your accuracy. So if you're okay to tolerate in certain applications that kind of degradation, it will be, I think it will be phenomenal in terms of robustness. Yeah.
Thank you.
Dhireesha, just to add to Alex's question, sorry. So the non-idealities you're talking about are the non-linearities of the response or mismatch between the memristors?
We looked at both types. Yeah, so there is mismatch across the devices, right? And we looked at that for the CMOS devices, what happens if you have these different types of mismatches in the lens and other factors. And that gave, I think this was like very early on that we did. We combined both of those models in our analysis, both the mismatches in the transistor devices, transistors, and also in the memristor response itself. And we also looked at, I think in the robustness analysis, we also looked at what happens if something gets stuck at a certain value. I think that's what I was showing in the stuck at faults. Yeah. So yeah, it's kind of different different types of studies we have done to see that it works well with those stuck at faults, with mismatches, and also variability within the device that you have in the responses, or the biases to certain switching and so forth.
Dhireesha, there is one more question that has come. Like, is there any maximum limit for the count of cells?
In the Htm architecture?
Yeah, I think so.
Yeah, so it is really, it's an interesting question. So we were bound by the compute and memory resources of the system that student was simulating on. But in general, it's a scalable architecture. But in a sense that you can go up to 2K cells in a single mini column. But a lot of times, I think, for the problems that even at the algorithm level, what Numenta is doing, they are not scaling the cells to that level. So usually it is like up to 10, 20 cells. And the idea is that probably you would want to go to higher levels. When it comes to that type of computation, you might want to go to higher levels of abstraction, as in add an entire stack of mini columns at a different level. So for a lot of practical applications, we haven't seen the cells grow significantly in a mini column. There isn't a need for it yet.
Thank you. I think there is one more question. Can you comment on the stability of the tuned synapse?
I do not understand. Stability of the tuned synapse. As in the metaplasticity model, or?
Not sure what is the... Sahiba, can you clarify that? In the metaplasticity model.
Yeah, so the synapses themselves are stable, right? What we are trying to say is that you can almost think of that synapse having multiple metastates, right? It's a small mini network by itself. So what we are saying is that by kind of giving this probabilistic hops from one metastate to the other, and kind of deciding what that probability is to different metastates, we are giving like a higher stability to the top metastates. And the lower metastates then become more plastic. So basically you're trying to make it harder to jump to a certain level and easier to jump to a certain level. That's what it is, right? The plasticity that you're trying to give is making it harder or easier for those transitions to happen. And that kind of helps in retaining knowledge from the past for a longer time, because you're making it harder to jump or hop onto the certain meta states. So if your question is, well, because you're adding all these meta states, does the synapse lose its stability? I'm trying to extrapolate based on your question here. The synapse would be still stable because this is a behavior that is observed. Metaplasticity is a natural phenomena that is observed in the brain. It actually gives the network more robustness, and it's a Hebbian learning mechanism, in fact. So it does give the system stability. It's just that it is so much more complex when we are thinking of hardware implementations, but definitely it gives the system stability.
I think we'll close with that. And if there are more questions, please type it in and we'll pass the questions to Professor Dhireesha. Okay, Bhaskar, do you want to close it?
Thank you very much, Dhireesha. It was a very interesting talk. And you started with some of the simpler concepts which our master students would have loved. And then you went into very deep. So I'm sure they by now should appreciate the simplicity as well as the complexity of the research work, which we all are hoping they will undertake. Thank you very much for that. And thanks to all the students for waking up or staying up till this late night, at least the ones in India, the ones in Europe, this night is still young. We will see you guys again tomorrow at the scheduled time and for a panel discussion followed by lecture on neuromorphic circuits. Have a good evening. Bye.
Thank you. Bye.
Thank you.